Okay, so if we have some distributions that tell us what is the probability distribution of H, we can easily use any sampling technique like Gibbs sampling to sample from it. Why? Because now each one is independent on the other, and this will be verified by proof. Okay, and this is the only advantage about removing these lateral connections. When we remove these lateral connections, it is called
Boltzmann.
Restricted Boltzmann machine, because we restrict it this way. Okay, so what is we want to calculate P of H given X, because in the previous slide I say that when we remove these lateral connections, we can easily sample from the distribution P of H given X, given an image. What is the probability of H? But first tell me, P of H given X, is it a matrix, is it a vector, is it scalar? P of H given X.
P of H.
No. Why is a matrix? P of H given X.
It's a vector.
You saw of it like we have two variables, so we should have a table. Okay. If I tell you what is the probability of P of H? P of H is a matrix or a vector or P of H? H. Is H a vector or a matrix?
H is a vector
Of
1,
three.
2, 3, 4, 5, 6.
H is this number. 3.
So each
H is from 0 to 3, and X is from 1 to 2.
But you said that each weight has two variables, so maybe say
H is the hidden layer itself, not the weights of it. The weights are W. Okay?
but as there is 3 hidden layers, there will be
Not layers, neurons.
neurons. Sorry.
Yeah.
There will be 2 output neurons.
No, we do not have any output neurons until now. We have visible layer, input, and hidden layer. We do not have any output layer until the moment. Okay?
I would like to say with
All what we need is this machine will represent P of X for us. There is no meaning for output layer here. Okay? So H is a vector of 3. So what is the probability of H? Is it a vector also? Yes. It is the probability of this. This is the first element of it. This is the second element of it. This is the third element of it. So P of H is a vector of 3. 3 numbers. What is P of, for sure P of H is a distribution, it's not a number. I mean P of H equal 1 is 3 numbers. P of H is 3 distributions. Okay, P of H given X. It's all the vector. We just constrain the fact that we are getting the probability of H by saying that X is habit. Okay, so this is a vector. We need to know P of H given X, which is a vector of 3 elements, and we know from Bayesian rule that P of H given X is equal to P of X and H divided by P of X. I think you know this rule or not? You remember it?
Yes.
Okay. We can prove it by giving some bold example and some visual examples, but if you know it, I will not do it. Okay? Okay. Do we know what is the probability of X and H? Yes, we already assumed it. It is e to the minus energy over the interactable term Z. Okay? Do we know B of X? No, but we can get it by total probability over B of X and H. What is B of X? B of X is the, what do you think? If you have, we have, yeah, this is B of X, right? B of X is you should do total probability over the other variable. Okay, so here is the summation. over H, but here we should write I or J or K. This is why we say H dash. Okay? And we write B of X and H here. Okay? Good. So Z is a constant. It will be cancelled with this. And after this, we remove E and write its equation that we already know. This is the equation for E that we assumed from the beginning, and we must multiply it with the minus. The same here. We will find that there is some term that does not depend on H here, so we can take it a common factor, and it will cancel with this. So C transpose X and C transpose X will cancel each others. Okay. Afterwards, we will do some separation because, okay, H here is a vector or a scalar. H here is a vector or a scalar? A scalar. H is always a vector of 3. Okay, if we have 3 hidden layers. Okay, so H here is still a vector. H here is still a vector. So we need to do summation over all the possibilities of the vector. So this is why we split this vector. This is the vector H. It contains H1, H2, H3. We want to get rid of H and use H1 and H2 and H3. Each one of them is scalar. Okay? So when we say HK, HK is scalar. So we get rid of the H here by adding a group of additions and an addition here that gives HJ. So HJ here is a scalar, and after this, we if you have e to the power something plus something plus something, you can say it is e to the power the first thing multiplied by e to the power the second thing. Yeah. Please, to speed up things, when you see me going to this while you are knowing, tell me it's okay. So e to the power something plus something plus something is equal to e to the power the first thing multiplied by e to the power multiplied by. So this is why we can remove this addition and put here a multiplication. Okay, so this is by over the same j here, and because we can rearrange all of parts of this does not depend on this summation. It depends only on a single summation, so we can rearrange these terms in this way. And after this, we will find that we are multiplying the same term with a single variable that is changing. So we can modify this by adding the by symbol. And because here we are multiplying things over j, here also we can take the pi as a factor. And we will find that b of h given x, which is a vector, is the multiplication of things over j. This means that b of h given x is equal to e to the power h1, w1, x plus b, j is always 1, multiplied by b of, multiplied by e to the power h2, w2, x plus b2, h2, multiplied by j equals 3, multiplied by j equals 4. It seems that we are having b of h given x, h here is 3 elements, is equal to some term multiplied by some term multiplied by other term, which means that we already know that this neuron is not connected with this, so they should be independent. Okay, so we know that b of h given x is equal to b of h1 given x multiplied by b of h2 given x multiplied by b of h3 given x. Okay, so we can say that the term here is equal to bhk given x. So we say that this term here is equal to b of k given x. So this is hj, not hk. It's any element of the vector k is equal to this. Okay, if we h can have each element of x can be 1 or 0. If it is 0, if you put here 0, you will get something. But if you put 1, you will have this equation. Actually, hj will disappear. Did this remind you of something? This thing here, does it remind you of something you have seen before? Say it at least. Sigmoid. Yeah, this is the equation of the sigmoid. Sigmoid of what? Sigmoid of what? If you don't see the font, say me the thing that is above the E or. Yeah, exactly. So it is sigmoid of what's here. Okay? So it is sigmoid of wjx plus bj, which is a very valuable conclusion. Okay, given x is a vector or a single number? Is a vector. Hj is a number or a vector? Number, exactly. So given x, I can tell you very easily what is the probability that each one of these is equal 1, or accordingly the probability that each one of these equals 0, because it's either 0 or 1. So if I know the probability that hj equal 1, I can say, okay, 1 minus it will be the probability of bhj equals 0. So this is a very good conclusion to catch from this slide. Give me x, I know b of h1, I know b of h2, I know the distribution of b of h3, and hence I know the distribution of p of h, which is composed of 3 distributions. Okay? So lots of math, but this is the conclusion to catch. If I give you x, you know the distribution of h. Okay? We agreed? Do you have any, did you dislike anything here? Or disagree about any step? Okay. Now we need a way to train this network. What I was proving in the previous slide is just some fact that will help us training the network. But it doesn't train the network. But it's a fact that will help us. How we provide an algorithm to train such network. How did we train the multi-layer perceptron? From where did we start? We have a multi-layer perceptron, lots of variables.
States.
Sorry?
We started with random states.
Okay, this is the first step of iteration. But to get a learning algorithm, how did we figure out a learning algorithm? What is the first step we did? It was motivated by the objective that we need. The error. Exactly. We defined an error function, and we wanted to differentiate it, equate it with 0, oversolve the problem. Okay, let's go for gradient descent. The same is here. We want to define an error function and differentiate it with respect to all the weights, and we will reach the conclusion. And the loss function that we are going to use here is the negative log likelihood on all the data. We have lots of data. So we have x1, this is the first training sample, x2, second, x3, x4. In general, it is xt. And we need to minimize this term. What's the meaning of minimizing this term? I have copied a good graph for you from Google. Let's see the equation of minus log x. This is the equation of minus log x. which means that if x is 1, the value is 0. Okay? If x is less than 1, the value goes high. Okay? And this time, this is x. So if the probability of this training image is 1, the loss is 0. It's very good loss. If the probability of this training sample is very low, we have high loss. Okay? And this is what we need. We need to model P of x according to the training data. If we ask the model, what is the probability of this training sample? It's trained, and we ask it, what is the probability of this training sample that you trained? If it is trained well, it should give 1. The probability, my belief about this training sample is 1. If it is a random model and you give it an image from the training data, he will say the probability of it is 0.5. If you give it a test data that he didn't see before, he will tell you the probability of this data is also 0.5. Because he does not have any belief about the training data. But if he has a good belief, he should tell you that the probability of x equal xt is a part of the training sample, is very high. This is what we aim for. And if this is happening, we will have this loss being minimized. Okay? So let's pause here and digest all of these concepts, and feel free to ask any questions, as stupid as you might think it is. Or I will ask you to make sure that we are in the same line. Because if I continue and you do not understand this, you will surely fail. Okay. So what is the main purpose of a Boltzmann machine? If I give you a Boltzmann machine with weights, it's trained. What is the purpose of it? How would you use it?
Distribution of probability of output.
Exactly. So using this machine, you have a probability of distribution of the data it has seen. So you can, from this distribution, sample from it to let the network innovate and produce data that is like what it has seen during the training. It's like having a child and you give him images of cats, images of cats, images of cats. Until one day, without seeing any images, he can draw an image of cat. Okay? This is one way that we can use it. The other way is that we can use it to model images of cats, and afterwards, because we have the distribution, we can have an image and we want to know if it's an image of cat or not. How to know using this model?
Using the probability.
Exactly. How? Exactly?
As it gives us an output for the probabilities, we can assume with a probability above one threshold or something. This could be considered as a decision making.
But can someone help us more? We have an image and we need to know if it is an image of cat or not. And we have the model. You have the model. How to run this model as a black box? You said because we have the model, we have the probability distribution of x. What is x? In this case, if it is trained on images. X, what is the dimensionality of x here?
2 dimensions. 3. It depends.
It depends on? On? Sorry?
Depends on its type, the image grayscale or color.
Exactly. So if the image is 30 pixels by 30 pixels, we have 30 by 30 input neurons. This is x. Okay? So you can ask this Boltzmann machine, what is the probability of x equal some image? And it will answer you, because we said that this machine has a probability of x, right? So you can take this your test image and ask the distribution. What is the probability of this image? If it is very low, so it is not a cat, because this distribution is the distribution of cats. So it will give very low probability for non-cat images. Okay, if it gives very high, we can put a threshold as you have said and classify this as a cat. Okay. Okay. If I give you an image and I ask you about what is P of H given X, how can you do it?
Using the formula sigmoid.
Exactly. You will just apply the sigmoid and use this formula. This formula is function of the weights, the bias, and the X. It needs only the X. Plug in the X, it will give you the probability of H given X, which is a vector. Okay? Okay, perfect. Now we are in the same ground. So we have this loss function, and as we have said, assume that the training data is only one side. We have x1 on. Okay, so t here is only one. It does not have a range. We have a single image. This is the training sample. What do we want? If I give you the restricted Boltzmann machine, and you ask it, what is the probability of this training sample? And it gives you 1. If I give you a different Boltzmann machine, and you ask it, what is the probability of this training sample, and it gives you half, which machine is better?
We can't say because it depends on the training.
The training data is this image only. In two cases, I trained your machine on that image. I trained your machine in the same image, and you use that same image as a query. You ask the network, what is the probability of this image, and it tells 1. You ask it during testing, what is the probability of this query image, and it tells you half. Which one is better?
Same network.
Yeah, the same. Sorry.
Is it the same network?
No, I gave him a network. I trained it somehow. I gave him a network. I trained it in a different way. The same image is used for my training for post networks. The same image is used by their deployment, and it is the same. We only have one image in the row. The same image I used for training, they both used for testing.
The hidden layers.
So this is not the question. The question is which model, which machine is better?
So it's
one of them is better because we use the same picture. So how can
okay, can you propose some other approach that tell us which one is better?
use another picture that we don't use it in training?
Okay, if they did so, he decided to use a different cat, and he shared the same cat with our colleague. So I trained in one image, both models, and both of them has image 2, not used during the training. So when he asks the my Boltzmann machine, what is the probability of this image, it gives 1. When he asks what is the probability of that image, he gives half. Which one is better? She catches the line.
I think that the first model that you give 1.
Exactly. Because you trained it on cats, and when you ask it about the probability of cat, it says, yeah, this is the probability of cat. But here, because we are trying to figure out a metric based on the training data that tell us if the machine is good or not, we do not. We will train using this training data. So our metric should be a function of training data. We are training now. We do not have any testing data. So we need to work the other way. We need to use single image. The same image I used for training, I will share it with you to use it for testing. I will share it with you to use for testing. Okay? And I'm hoping for, if I understand the data correctly, I will give 1. If my model, imagine if that my machine is not very good and it even didn't look on the image. It took the image and it didn't learn anything from it. Will it give 1? It will give 1 if it has learned the image very well. So if you give it the same image, it will give you 1. Okay? So this one is better. And this is exactly the metric we used here. So if B of x is 1, this is B of x. This axis is B of x. If B of x is 1, what is minus log B of x? It is 0. Perfect. If B of x is 0.5, what is minus log B of x, it is higher. If it was 0, if P of x, which was in the training data, is 0, the loss is infinity. Okay, this is a convenient metric. Let's differentiate it and figure out how we'll use it for figuring out the training rule. When you differentiate it, you will differentiate it with respect to what? With respect to this weight, then this weight, then this weight, and equate all of these equations with 0, and you will end up with an over-solved problem. Okay? When was the first time do we hear this? Before? Where? Yesterday. In which part?
So the problem with dropouts.
Sorry?
With the dropouts.
No. Not the dropout? With? Not with linear regression? Cedric, my friend. Don't let me down.
I'm less sorry.
Try to catch. Okay, so
the parameters were like.
you know it, but you cannot formulate it. When was the first time to hear that we have an oversolved problem?
Oversolved. First time.
Yeah, I'm sure you know the answer. I'm sure you know the answer. When we have been trying to train an MLP, what did we do? We differentiated the cost function with respect to all parameters, and we figured out that this is an oversolved problem. This is why we went to gradient descent. And here it is the same. We are facing a group of equations that is oversolved. So what can we do? Let's see. Let's firstly figure out how to differentiate this, and I will tell you how to do the training in this case. We will not use gradient descent. We will use another method called contrastive divergence learning algorithm. Let me briefly tell you what is contrastive divergence learning algorithm. Okay, this is the loss. We are convinced. If we minimize this loss on one training data, we can redo the process again on every training data, and we learn all the training data. So we will learn only one training sample, which is xt. So now we do not have this summation over all t's, and this t is for averaging. So we have one sample, so we can remove all of this. So we need to differentiate minus log b xt, which is a single training sample, with respect to some parameter called theta. Theta can be any weight. Okay, so differentiation of the log is 1 over what is inside the log, but I cannot see here. Here we didn't differentiate it. Here we try to expand b of xt. What is b of x? It is the summation over all possible values of h of b of x and h. Remember? Here it is. B of x is the summation of all possible values of h for b of x and h. And what is b of x and h? What is the equation of b of x and h? We assumed from the beginning its format. We assumed that it's e to the power minus e over z. We assumed it, and why did we assume it this way? If you digest this slide, you have Boltzmann machine. So be patient. Don't lose hope. Try to follow up. Okay, we say that p of x and h is equal to e to the power minus e over z. Why? Why we did say this from the beginning? The first slide at Boltzmann machine, I said this to you. Why?
Decreasing function.
Exactly. Because we said that we have an energy, and we need to minimize this energy, and this is why we choosing an equation that is inversely proportional. So P is inversely proportional with E. Okay? Okay, so let's write it here. This is P of x and h, e to the power minus e over z, and we do the summation over all the possible values of h to have b of x. So we replaced b of x with this. Okay, where x is a specific training sample that we know. So let's continue. We can okay, now let's take this denominator and put it if you have log something over something, you can say it is log of first thing minus log of the second thing. So this is minus log of the denominator minus, so it's plus log of the denominator. Very good. Right now, until now, we didn't do any differentiation. Very good. Let us continue. Now we will do the differentiation. The differentiation of a log is 1 over what is inside and multiplied by the differentiation of what is inside. So 1 over, this is a minus, and 1 over what is inside. And here we need to differentiate what is inside. And to differentiate what is inside, the differentiation of e minus something is to write it as it is and differentiate what is in the power. The differentiation of minus e is minus differentiation of e with respect to c. We didn't calculate this yet. Okay, so we switch this to here. Plus the second term, the differentiation of the log at the denominator and the differentiation of what is inside and its differentiation of e. So the e is written as it is, and we differentiate the power. The differentiation of the power, the minus is here, and what is remaining is dE by d theta. So now we need to figure out what is dE by d theta, and we are done. Let's even simplify this more. So this minus is cancelled with this minus, and this term is here. And we can say that this term here is b of h given x. How we say this, if you remember? Yeah, here. b of x given h was equal to this divided by this. Okay? So remember this shape, e to the power minus e. The denominator is e to the power minus e also, but with summation over h. Now we replace this shape here, with p of h given x, and this summation is here. Okay, what about this shape? Does this remind you of something? Does this remind you of something? What do you think? I need an answer, please. E to the power minus e over summation of the same over all the possible values of x and h. Okay, someone tell me what is the probability of h and x? What is the probability of x and h? Please, can you tell me, but raise your voice. What is the probability of h and x? We assumed it. What was our assumption, Jeremy?
Probability of x and h exponentially 1 over z exponential minus the energy.
Exactly, and what you can see here? What is this?
This is the z term.
Yeah, this is the z term.
Yeah.
What is this? Is the denominator. So what are these?
The probability of x and h.
Exactly. So we will remove this and say probability of x and h. Okay, and this summation will be here. Okay.
Can we simplify the because here the numerator and denominator of the same.
Yeah, here we have a summation over all possible values of x and h. So this is it. This is it. And here we have e to the power minus e. E to the power minus e over z is b of h and x. What's confusing?
Yeah, if you remove your n, there's the same sum, right?
Okay.
And
It will be here. We didn't remove it. We didn't remove this. This is this. We didn't simplify it.
No,
yeah, but why don't we simplify it?
Can you simplify it somehow?
Well, if it's the same thing, it's a division of the same term and it gives what? Am I losing my math?
that was not so. We're not simplifying that.
I catch the point now. And this is actually a good point, but we are missing something.
For me, it's the multiplication, which is
Just for one.
cannot.
Which multiplication? No. This is summation, and this is the same summation. You can cancel with each other. But the trick here is the indexing trick. Okay, let's figure out where does this come from, and where does this come from? Because I may have dropped some dash here.
So this is
So give me one moment.
Go up.
So both this and this are coming from here.
They're coming from the.
So we have the same issue here.
Yeah.
So let's go to the basics. So this is xt. This is xt. Okay. I ignore this. So this should be xt. And this should be x in general. Because this is z. So this is xt. And here this is xt. And this is xt. Something missing. Because I have wrote this proof, I didn't copy it from anywhere because it's described very bad in books. Really try to read about it. So I know this conclusion. This is why I wanted to reach it. This is how I reached it very fast. But I missed something. So let's give like 4 minutes on this so I can correct the slides.
I think you have double summation on Z, not only one. You have the summation over 8. Yes, that's right. It's a double. Okay.
Which summation?
When you replace Z.
Yeah,
yes,
Z.
You have double summation.
No, Z is yeah, it's double summation over x and h, and here it is. It's double summation. What's the problem? The problem comes from here. The differentiation of we have a problem converting this to this. We need to inspect this. This should be not this. Denominator 1 over denominator. I think, yeah, this is not correct. Okay, I might have find it. The differentiation of the log is that you take what is inside and put it in the denominator. So the denominator does not have any problem. And this is the minus. Okay. So here we need to differentiate this. Let's differentiate this. This is the addition of different terms. Okay. So the differentiation should be the addition of all of this, such that the summation of h is over all of this. Okay, so let me modify this. Sorry, sure. Okay. So let's remove this bracket here. Oh, it's getting hot. Okay. It's hard to edit using Word. Okay, I did it. Minus. And let's do the second term. I have gave this training before at Cairo University, at the American University in Cairo, and in Valley, Egypt. And I remember that I was using the same equation. I was the first one to catch my mistake here. So let's see it now. So now this is inside the summation. Jeremy? Yeah. So convince it. This is inside the summation. Okay. Okay? So we cannot say that we can cancel this with this. And the same is here. We cannot cancel this with this. And the reason why all of this is inside the summation is that we are trying to differentiate added objects. So each element will be this multiplied by this plus this multiplied by this, and so on. This is why the summation should be over the two terms. And now we can say that this is b of h and x, and this is b of h given x. So thank you so much. And this is what we have reached. The differentiation of the cost functions that we are convinced it is good with respect to theta is this. Here we have what is called the positive learning phase and the negative learning phase. Okay? And I tell you how Mr. Hinton has suggested a way to train such networks that was not feasible before he tell us how to do it. We will use contrastive divergence learning algorithm, and the way how it works is that we do not have any problem evaluating this term, but we have a problem evaluating this term because it is a double summation over x and h, which is intractable. Because when we say that we have a problem with z, and we say it is intractable, it was because of the same reason. It was because that it was a double summation over x and h. Here we have the same thing. So we will use the CDLA algorithm to put some estimation for the value of this negative term. Also, we will use some trick to evaluate this term. Does anyone is familiar with this with the term here? When we multiply some probability over all the values of it and multiply with some number, what is this? Yes, it is the expectation. If you have a distribution, like this, this is a discrete distribution, but the concept is still valid. Assuming this is x, and this is all the probabilities of x, this is half, and this is 0.3, and this is 0.2. This is b of x, and this is 2, this is 3, and this is 4. Okay? If this is b of x, and I tell you what is the mean of x, mean of x, the fancy term for mean of x is the expected value or expectation of x, of p of x. Okay, what is the mean of x? Can you calculate it? So the probability that x equals 3 is 0.5. The probability that x equals 4 is 0.3. The probability is 0.2. If we resample from this distribution many times, what is the average? What is the mean values that we can get? Can you provide something? Simply, we can do a very simple trick to multiply 2. Exactly, Steve. So 2 by 2, 2 by 0.2 plus 3 by 0.5 plus 4 by 0.3, which will give you some point here. It's like 3.3, which is really the average. So here we are doing the same. It is the summation, and we multiply the probability of something. By the way, what if I tell you what is the mean of x squared? How can you do it? Can you suggest an multiplication history to solve it? I will give some. Some less for my friend. What do you think? Huh? Someone was saying, you can. Yeah, what do you think? Okay. What is the probability of x squared? Let's write here. What is the probability of x squared given that this is the probability of x? If x squared is 2, what is the probability of having x squared is equal to 2? Yeah. This means that x was 1.4, so x squared is 0.2, and I know that the probability that x is 1.4 is 0. So the probability that x squared equal 2 is 0. What is the probability that x squared equal 4? Ah, this means that x was 2, and the probability of having x is 2 is 0.2. So the probability of having x squared by 4 is 0.2. Okay? And so on. Ah, so this formula, so 9 will be 0.5, and 16 will be 0.3. And if you use this, you will find that the mean is 4 by 0.2 plus 9 by 0.5 plus 16 by 0.3. Ah, we could have figured it from the beginning. You need the mean of x squared. I will not replace all of the x's with x squared. You need the mean of x squared over 16. Okay, I will replace each x with x squared over 16. Okay, so if you need the mean of d of e over d of e by d theta, okay, this is the mean of it. The thing that you are multiplying the distribution with is the thing that you are searching for its mean. So we can say that this is the expected value or the mean of this over this distribution. Okay? The problem with this is that we have double expectation. This is why we need to get rid of x here, and we will see how we will get rid of this x.
I'm sorry.
Yes,
the negative phase is intractable, but the
yes.
first phase is still sum over all the possible hidden states of the network.
Yeah.
Does that imply a large constraint on the network? Because it could become intractable if you have more than a binary state, or if you have many hidden neurons.
The simple answer is yes, but let me think about it. If we have many neurons at the hidden layer, and no, I don't think so, because if this is an unpractical assumption to have a very big number of hidden states, but if you have that unpractical assumption happening, so it is the case. So summation over h will be intractable and inconvenient, but x also will be a major problem because of two things.
Yeah.
Because of two things. Usually x is much larger because it's like an image or something, and most importantly is that when you do double summation, you are repeating h
Every time. For
x times.
Yeah.
So this is the problem. Okay. So if x is 100 and h is 100, summation over h will be 100 elements. But summation of h and x will be 10,000. 100 by 100. So even that x is the same length of h, which is unpractical, because usually we need to encode these features in a smaller number of hidden neurons. But assuming that they are the same number, it will also be no comparison between the double summation and single summation. Okay, so we have two terms. Let's firstly get this easy term, which is easy now after you understand this. This is the term. This is the term of the positive base. We can say that, let's calculate this. This is very easy to calculate. We want to calculate dE by d theta. And theta here should be any weight of this. So any weight of this can be wjk. It connects neuron k by neuron j. And what is E? What is E? Sorry? Yeah? We are learning here. No one get. What's E? Yes?
It's transpose multiplied by the weights.
Exactly. Because it's an assumption that we started our lecture with. Okay? So E is minus B transpose H plus minus C transpose X plus the factor with the W. This is the first equation we have. Maybe we can briefly remind you of it. This is the first slide. So this is E. We assumed it. Okay? But this is a vectorized format. If we rewrite this in a non-vector format, we will find that we can write it with these summations. And when we differentiate all of this with respect to a single weight, we will get that only this term is remaining. Okay? The term that remains, that has the hidden layer associated with the neuron, wjk, and the input layer associated with the input neuron x. So this looks very complex, but actually it's very easy. So let's take it because we need it, and we substitute on the positive phase term. So here it is. Okay. I don't know what is the hint I'm writing here. Okay, yes. These summations are reduced. It's very easy. Okay. Here we are doing summation over H. What's H? Is the vector or a scalar? Sorry? H is a vector or a scalar? It's a vector. So we are doing a summation over the vector x. So we substitute here with H with some value, and also here the vector has different value and different value. And we find that this term is a function only of Hj, and it's elsewhere it is 0. This is why we can reduce this summation to be only testing the vector, the element Hj. If we are speaking about this weight, so we are only reducing the summation to be testing the conditions of this neuron only, not the whole vector. This is why we converted this summation over a vector into summation over a scalar here. And afterwards, we try the both values of H equals 0 and 1, because we said H is binary. If it is 0, this term is 0, and if it is 1, this disappears and this minus comes here. So it's minus P Hj given X k, x is the training sample, don't forget, multiplied by xk, which is coming from here. So let's see how we will modify the weights according to the positive weight. We will multiply by eta, some learning rate, multiplied by the vector. If we need to, it depends on the value of j and k. If we want to modify this weight, so j is equal for this weight. Which weight is this? It is this weight. So j is equal 1 and k is equal 1. So the positive phase is saying minus p h1 given x1 multiplied by x1, and this is the term for the positive phase. If we vectorize it for all the neurons, we will get that we can update all the weights using this vectorized format. Okay? What's remaining here is the negative phase. Let's see how to get it. We may So can you see the difference between here and here? If we want to remove x from here, we can enforce, instead of doing the summation over x, we can approximately remove this summation over x and put some value that is representative of x. How is this happening? It is by asking the network about its belief. So delta W will be the positive phase minus the negative phase. The positive phase we have already obtained from here. Okay. H here is P of H given X. We name this as H. So H is P of H given X. And X is the same. So we will repeat the same equation. So this is the positive term. We will repeat the same equation, but instead of taking the input training data, we will search for what is called X hat. X hat is the most common probable X that the network can give to you. And how we can do this? I think I have a slide for this. Yeah. Okay. So we will input the image, the training image. And using this, we can get P of H given X, which is, this is X. We put X. Can we calculate P of H given X? How? It is a sigmoid, so we can calculate it. Let's sample from this sigmoid. Okay, let's sample from it. And so now we have H. Now we have a value for H. And we can get P of X given H very easily, as you have seen here. We now know H. Now we know H and X, so we can calculate this, and we know the probability of X, so we can easily calculate P of H and X. So we get P of X given H, as I have shown to you, and we sample from it. Okay? So we will give the network some image of a dog. It will calculate P of H given this dog. Okay? And given that distribution, I will sample from it. I will sample 1 point from it. And given that sample, I will know what is the probability of image given this value of H. Okay? So it's like the network is trying to redraw the input image again according to its belief. I should keep doing this, keep doing this, keep doing this until the image resulted by the network is not changed. Okay? And that x, that resulted x, after k iterations, k is a very big number, I will name it the negative sample, which means that this is the belief of the network about that input image. So it takes the input image, construct some belief, and we sample from it. After this, we calculate what is the probability distribution of x given that edge. We sample from it, and we enter that sampled image. After we repeat the step, and the image keep changing until the image is not changing anymore. And we name this the negative sample x prime. And we will use this x prime or x dash to evaluate the negative sample term. As an approximation, we will consider that the second term is exactly the first term, except that it is taking the average or the negative sample, the average sample or the negative sample instead of the training data. So let's revise what we have said again, very briefly. So, why it's not showing? Yeah. So, in the negative phase, we will replace the sum over x with an estimate point obtained by k iteration Gibbs sampling. We will do the sampling using Gibbs sampling. It's a technique to sample from a distribution, starting from clamping xt, which is a training sample. So it will be positive phase term, but with xk instead of xt. So we will put xt and obtain some value called the negative term xk, and we will treat this term as if it is exactly this term, but at x prime or x dash instead of xt. And we have evaluated the positive term, so we repeat it again at the negative term, but with it changing, instead of xt, the training sample, we will put x prime. So let's be more practical. Now we finished the equation, we finished the theory. Let's be more practical and tell you how to train a Boltzmann machine practically with code. This is the theory. With code, yeah, please.
We always also all the equation that we saw in was for the Boltzmann machine, but you talk about the belief of the network too. So deep belief network and Boltzmann machine are separate things, or
yeah, we will come to DBN later on. Okay, very good. So we need two things here. For the positive term, we do not need anything unless x. Given x, we can calculate everything that's related with the positive term. But for the negative term, we need to do this operation until we obtain x prime at reasonable k, because that x prime is needed to calculate the negative term. Okay, and delta weight is function of, it's the equation of delta weight again. Is this the positive term minus the negative term? So we need to do this operation until we get the negative sample, but by practice you can do this only once. Once you get the image and get p of h given x and sample from it, and using this sample get p of x given h and sample from this p of x given h, this is x prime practically. So one iteration k equal 1 is always enough. So what we are doing in case of positive term according to this equation, we are increasing the weight with some factor, and during the negative phase we are decreasing it with some factor. So it's like we are incrementing the weights between an active pixel and an active feature. When an active pixel here has a connection with a feature here that is active, that's 1, we increment the weight, because this is the equation here. If we have an active x that corresponds to a high probability of having an active hidden neuron, this term will be positive, and w, this is delta w, by the way, it's not that. Delta w will be positive. So we are incrementing the features that incrementing the weights that connect is active pixel in the training data and active pixel in the binary hidden layer. But during the negative term, we are decrementing. We are decrementing the weights between an active pixel and an active feature. Imagine if I give the net, this is important by the way. Look, this is important. If we give the network some image, okay, and given this x, we calculate b of h given x, it's sigmoid. We sample from it, and given that sample h, we calculate b of x given h. It gives the distribution. We sample from it and get a new image here. If this image is the same as this image, what does it mean? We should stop training. The network now can understand the image from this. It can construct the same image. We should stop the training, and this is what is happening. Here we will reward the weights connecting active pixel here and active pixel here, and by some value. And when we end up having the same image here, we will decrement each pixel having an active pixel here and active pixel here. So we will end up not modifying the weights. What we have increased here, we have decreased here. Okay. So initially, assume that this is the space for all the possible images, and this is the space of b of x. Initially, you will find that this curve is flat, so the probability of generating any image is possible. We didn't learn yet from the data, but with time, if you train this network on images of 2, images of 2, images of 2, you will find that at this value of input images, you will have a very high probability. Okay? Okay, very good. So to conclude, for each training sample xt, we generate a negative sample using k steps of depth sampling starting at xk. K steps can be only one step. And we update the parameters as follows. We have a positive step and a negative step. And if the network is able to generate the same image, we stop training. The bigger k, the less fast the estimate of the gradient will be. For sure, you should wait for long k, but practically it doesn't affect the performance so much. You can imagine for a second that an RBM that was only fed images of elephants and dogs, only see elephant and dogs, and which had only 2 output nodes. Okay. The question the RBM is asking itself on the forward pass is, given these pixels, should my weights send a stronger signal to the elephant node or the dog node? This is assuming that the network will split the knowledge between 2 nodes, which is not very practical. So during the forward pass, there is an image, and the network is asking itself, I have some connections going to the first hidden layer, the first hidden neuron, and I have other connections going to the second. And it asks itself, should I increase the weight, these weights, or these weights? And okay, and the questions RBM asking during the backward pass or the negative pass, given an elephant, which distribution of pixels should I expect? Okay, we know that it's simultaneous probability of x and h, the process of learning reconstructions and sense learning which groups of pixels tend to co-occur. Okay.
Sorry, just
yes,
trying
please.
to understand something about what this machine is. The hidden states are binary in the examples, but not necessarily binary.
Not necessarily, but this will make things take more time, and practically everyone is doing it binary.
Okay. The inputs are, if it's an image, for example, are not binary.
You can still work, but usually it's binary also as well.
Okay.
You convert it to grayscale.
Binary inputs and binary states. There are therefore activation functions on the neurons to ensure that the states are binary.
Normally there is no activation function in the neurons here. The neuron itself is holding a number. There is no activation function here, but you can.
So the binary state would be either the number is null or non-null, or how do you determine a binary state based on a weight?
Each neuron has a value, which is 1 or 0. This is why we call it it's a binary neuron.
But the weights are
Continuous.
binary as
Continuous.
well?
No.
Continuous.
Yeah.
So you have a binary input, for example, 1, you multiply it by a weight of 3.
Okay.
How do you
Remember, it doesn't work like this. If you have an input and you want to calculate the edges, you do not do this multiplication.
Yeah.
These weights are not multiplied by the input. They hold the distribution somehow. If you want to calculate this, you calculate b of h given x. It's a sigmoid. Okay. It gives you a distribution, and you sample from this distribution, and this distribution will be discrete between 0 and 1. So it will give you the probability of 0 is 0.5, 0.6. The probability of 1 is 0.4. So you sample from this distribution. H is always 0 or 1. Okay?
Okay.
It's completely different from the definition of neurons that we have been discussing. But it's interesting. Now the practical part. We have database of tools. Images, grayscale images of handwritten tools. Tons of images. And we give it to the RBM and tell that RBM learn. We have we have 15 hidden. We have 15 hidden. I have generated these images by implementing the code, by the way. So we have 15 hidden nodes, and how many input nodes? How many input nodes should we have? It depends on what? The size of the image. It's a grayscale image. Let's assume it is 40 by 40, so it is 40 by 40 input neurons. This neuron is connected by all the 40. So, if we want to draw some image that say this is a feature extracted by this neuron, how to draw it? We can draw an image of these 40 by 40 weights, right? And if they are bright, if they have higher values in some places, this means that it is interested in these pixels. So the inputs here are pixels. The brighter the weights is, that tells that this neuron is interested in these pixels. If it is small, so it is not interested. So we can draw an image that represents all of this neuron, and this image will tell which feature is this neuron extracting. So before learning, or after how many iterations? After very small number of training iterations, that was the features extracted by the 50 hidden neurons. But after time, not after time, this is the final features detected by the neuron. This neuron was interested in detecting this part of the 2, because the 2 is written like this. This part also. Each one learned this part, learned how to capture the blank area in the middle of the 2. So each one learned to extract a useful feature from the 2. Okay. So now this restricted Boltzmann machine RBM can encode the 2s for you. And if you give it a 2, an image, and ask him to get b of h given this 2, and sample from it. So you have some h, vector h, 50 numbers. And you calculate b of x given these 50 numbers. You have a distribution over x. You sample from this distribution and get an image. You will get an image like this. So if this is the input image, the network has a belief and can reconstruct it like this. What if we give it a new image that it didn't see before? So I gave it 3. And the construction was like this. It tried to capture in the input image the features that looks like the 2. So it captured this part and ignored this area, and it captured this part. So it is 2 that looks like the 3 you have inputted. I did so. Now I have let it learn on all the numbers. The data set now is all the numbers from 0 to 9. Okay? And after learning, I give it some image, and I ask the network for the reconstruction. So if it takes this image, it reconstructs it like this, which is converted it to 3, which means that it has a belief that it's 3 more than 5. This is reconstructed as this. This is reconstructed as this. What if we give it symbols? So the experiment was to give it symbols like this. It didn't see any symbols during the training. And it started to reconstruct images that look like the symbols. This was reconstructed as 0. This was reconstructed as 9. This is because it is circular, 0, 0. That was reconstructed. This was reconstructed as 8 because it looks more like 8. So the network has a belief about the data, and anything you show for the network is understood as part of this data. This is the word for it. If you give it a picture of this remote control, it understands this as one of the 10 numbers that it can understand. This is the reconstruction. If we do one round only of training, this is the reconstruction of this image. This is the reconstruction of this image, which is random. This is the reconstruction of this image. And after 1 round, these are the constructions. After 2 rounds, these are the reconstructions. After 200 rounds, this is the reconstruction. Okay. And after training, I wanted to visualize the features as we were doing here. These are the features after visualization. So each hidden neuron was expert in detecting a specific feature. This is detecting the upper circle of the 8. This is detecting the slanted edge of the 6, and so on. Not necessarily we should understand or justify these features as long as he thinks that they are the best to represent the data. It's okay. So what is deep belief networks? Deep belief networks is a stack of RBMs. So we have an RBM here. This is the bias because each neuron at hidden layer should have a bias now. And this is another RBM. And at the end we have a fully connected layer as usual. So if we want to do a digit recognition system, we can use a CNN from the start and train it on images, or we can train a restricted Boltzmann machine on all the images. It doesn't make use of the label. It throws the label because it uses only the images. But it will make an understanding or a good representation of these images. So this can be used as a very good feature extractor. And this is what we are doing here. One moment, please. So we put this restricted Boltzmann machine here because we know it's a very good feature extractor. And we can build more hidden layers. And at the end, we put 10 neurons, one represent each class, and we just do fine tuning. We retrain everything, but with the knowledge that the first neuron is making use of the zero digit ground rules, and so on. Okay, so we stack different RPMs, we put fully connected layer, and we do supervised fine tuning toward our application. Many times this is better than CNN because restricted Boltzmann machines has learned its belief about how the environment looks like. Also, this does not require lots of data as CNN. Yes, please.
How this one is different from a multi-layer perceptron, which has 3 even layers, each one of them with 3 neurons?
Okay, so multi-layer perceptron can never take the raw data. This takes the raw data and give you a very good results. Okay, this is the first data. Raw data. Yes. You cannot give the MLP the raw data. you have to do feature extraction.
Without the labeling, of course.
No, with the labeling. With the labeling in a supervised way, you should do dimensionality reduction for the MLB to work correctly. This is the first difference. Here we do not do any dimensionality reduction. This is the raw image. Okay. Second thing is that you can make use of tons of data that are unlabeled for training. This will be very useful. These are many the tools. Okay. Okay.
No, because in the Boltzmann machine the hidden layers was hidden. Now they are intermediate. But now they are looks like
yes. So this hidden layer is trying. This is the hidden layer of the input, and this is the hidden layer of the feature of the input, and this is the hidden layer of these features. So, and by the way, you train it incrementally. We train this, and we record the edges here to be used to train this, and we record the edges here to be able to train this. After we finish this, we have an efficient feature extractor represented by all of these 4 layers, and we use it and add fully connected layer and retrain only this area with back propagation to do the supervised data. So this is a black box as if it is a feature extractor, efficient feature extractor. This you can treat this as a black box. Now you plug in 2 or MLB as you like, and the MLB is using this good feature. It cannot use the raw data. Okay. Yes.
How does contrastive divergence compare to backpropagation in terms of training speed?
Yeah, the contrastive divergence is much faster.
Much faster.
Yeah. Because here we do not need to calculate any gradients. It's just a sigmoid, and we have a single step of K to calculate the negative sample. We do it in a single step, not K steps. So it is much faster.
Okay. So in terms of computation, it is faster. In terms of convergence, it converges also faster towards.
We cannot compare because they are used for different systems. We cannot compare one to apple to apple.
Okay. And a second question is what is exactly the difference, the key differences between restricted Boltzmann machines and autoencoders? I understand mathematically the restricted Boltzmann machines have a different representation than autoencoders, but once you start stacking them up to exploit them as a classifier, for example, then what is the difference?
Yeah, it's like asking what is the difference between logistic regression and linear regression. They do the same job. They learn from unsupervised data, but they are different techniques. Maybe the restricted Boltzmann machine is faster by experience, but some of them may excel in some application and other applications. But different methods to do the same thing. Autoencoders is another unsupervised way of learning, and they both can handle unlabeled data. This is, I think, what I can say about it. Okay. This also, if we give the network this image and ask it to resample to give us its belief, it gives this. And if we give it after some time, the network is trained already. We do not do any more training. So once we ask it to sample from this, it gives this. If we ask it again to sample from the same image, it gives this. If we ask it again to sample from the same image, it gives this. From the same image, it gives different shapes of zeros. How can this happen?
Different probabilities may be applied.
Be more specific.
If the output is defined to get the best probability, maybe there will be a perfect zero.
Exactly.
But as here we said, get one of the best ones, but not
we sample. we are sampling. We are not getting the best. If we are choosing the best X that maximizes the P of X, we will get the same zero. But here we are sampling. Not necessarily the X with the highest probability is picked up. Also the P of H, we are sampling from the P of H. This is why, given the same image, the network starts to innovate for you different zeros. If you give it this 6, it gives you all of these 6, but it doesn't give you 7. This is a very important, and it means that it understands that this is 6. It doesn't know that it's a class that you name 6, but you give it all of this data, 1s and 0s and everything unlabeled, and if you give it 6, it will generate 6s for you without any labeling during the training. If you give it 5, it will give you 5s. Okay? This is restricted Boltzmann machine. This is not deep belief network. There is no supervision, which is very, very astonishing results. These are samples that was not included in the network training, but was being correctly classified by deep belief network. So let us. We still have like quarter an hour, so let's discuss about recurrent neural network. It's a new topic, so refresh, please. So sometimes you do not need to learn from snapshots. Sometimes you need to learn from sequence. Let's see how this can happen. Okay, so until now we have a network that goes feed forward. Okay, but now we will have some recurrency. So we have a weight that connects this neuron with itself, and the same for all the data. Okay, this neuron has a different weight that connects itself with its output. The same here and the same here. So the output of this neuron now is coming from this input, which is coming from the current input, plus the previous value of itself. Okay, and the output of the next time step will be a function of this current input plus the output of itself during the previous time step, which was also function of the previous time step. So each output here will be function of all the history. Okay? So when we discuss about neural network, we do not look to it, recurrent neural network, we do not look to it anymore from front view like this. We will look to it from side view like this. So this is the side view. Okay? So this is the network from side view. This is a layer, and this is a layer of 3 neurons at the bottom. This is the layer where there is a recurrency. This is the layer that is above it, and so on. So this is a layer of neurons, but they are like this. Okay? So we can say that the output of the first layer depends on the current input plus the previous, plus some initialization of 0. But at time step 2, the output of the same layer depends on the output of the same layer but before, plus the current input, and so on. So this is how we unfold it via time. Is it clear? Okay, so from here on, we will use this terminology. This is the input layer, this is the recurrent layer, this is the output layer. Does this layer has any recurrency from what you see here? Why? From this figure, does this figure say that this layer has a recurrency? From where do you know?
No lateral arrows.
Sorry?
No lateral arrows.
Yes, there is no lateral errors here. So the output of this neuron depends on its input only. It doesn't take the previous value. But take care that this input is already a function of the history. Okay? So the output here is depending only on the current input. But the output here is depending on the whole history. The output here is depending on the whole history. The output anywhere above is depending on the whole history. Despite that, this neuron does not have any recurrence. Okay? But because it is after a network that has a recurrence. And this is a layer, so it takes from you an image. Imagine that we have a video. Okay? So here you can put an image frame. This is the input layer. Has lots of neurons, but we are looking from side view. So you put some video frame here, and you put the video frame at time t, and you put the video frame image at time t plus 1. So the output here will be function of the video, not a single image as we have used to do. Yes, please. Do you have a question? Okay, so now we have input sequence. This is a representation of the delay in terms of filtering. Okay, let's have an example. Did you hear the word language model before? Yeah. Language model. What's the language model? Language model is a language model. What does this mean? It is a model that is modeling a language. So it understands the language. We can train an RNN to model the language. How can this be done? Just provide it with tons of text. Okay, but RNN is like MLP. It should be trained in a supervised way. What will be the ground truth of each text? What it should predict? Okay, so let's formulate the problem as this. If we have some network that takes a text and can give me the probability of the next character, this is a language model. So the network can read text, and before it continues, it can tell you what is the probability of the next character. This is a language model. It's a character level language model. To construct a word level language model, given a text, stop. Ask the network, what is the probability of the next word? It will tell you the probability that the next word is 0.5. And it can be as with 0.4, or it can be like this. So here we want to build a language model on character level. So this is how we train the network. This is a layer, and this is a layer, this is a layer, and this is the type. So we'll put our training string here. We have 4 neurons, okay, and we will encode all the possible character in English with some binary encoding. So each character will be having four binary numbers to represent it. So if it H, we will put 1, 0, 0. If it E, we will put 1, 0, 1, 0, 0. If it and so on. We will have a table that translates each character to some input data. And we will tell the network that given this sequence, okay, the next character for the H is E, and the next character for the E is L, and the next character for L is L. So we will present our text for the input layer, and we put the ground truth the same exact as the text, but shifted in time by 1. So the network will learn that given this sequence, H, the most probable character is E. The next probable character, because L is most probably L. We are teaching it in this way. So our data is text. That text we use it as the training data, and we also use it as a ground truth, but we shift it with only one time step back in the past. Okay. And okay, we have some input. We have a desired output. We can get the gradient between this output and this input, and we can train this with back propagation neural net algorithm. If we can figure out what is the error between what is a good criteria for the error metric, and if we can differentiate it with respect to all of these weights. Okay, and we start the model from initial hidden state, because each time this hidden state, hidden layer want to get an output, it requires the input of itself one time step back. What about the start of the system? We should put zeros as the initial state. So start the model with its default hidden state, whatever it is, zeros or anything. Give it a burn-in sequence of characters and let it update its hidden state after each character. Then look at the probability distribution it predicts for the next character. This is to test the system. Once it's trained, how to test if it's good or not. You have the language model and you want to test if it's good or not.
You give it words.
You will give it some text. Ahmed is going to the university, and leave it. Let it predict the next character after the Y. Most probably it will be space. So it will predict the space. Give it the space as an input. So it will predict that university space, and it will consider the whole sequence, and it will try to predict the next character. So give it as an input. If your prediction is the input, what will be your next character? And the network will start to innovate text and tell stories and give you lots of wonderful things. So start the model with its default hidden state. Give it a burn-in sequence to proceed of characters, and let it update its hidden state after each character. Then look at the probability distribution it predicts for the next character. It gives you a distribution. You should randomly select one character from this distribution, because the output of the network is softmax, so it's probabilities. So you have a softmax distribution. Instead of selecting the maximum, you can sample from it. So after sampling from it, tell the net that this was the character that actually occurred. It means that give it to the network as an input. Tell it that its guess was correct, whatever it guessed. Continue to let pick up characters until booled. Look at the character strings it produces to see what it knows. And there is tons of interesting applications that's based over this. As example, we can find some.
How to tell the network that he is correct?
There is no way. If you train it on a language model like this, the way to test it is to give it a burn-in sequence and let it innovate. And after this, you read what it has written.
How to correct?
To correct it, maybe if it is bad, you can correct it by improving your training data, editing the network architecture, playing with the learning rate, and so on. But you cannot get a number of the correctness or the accuracy, because we do not have a clear test set. We have training test set text, and we give it to the network. So there is an interesting link here. No, not this one. Yeah. Someone has trained this network on 4.4 megabytes of Shakespeare works, all the works of Shakespeare. Okay, and after training, he let the network to innovate, and it started to write this. This is practical, by the way. You can download the source code and play with it. This is done by the network. This is written by the network. Nobody has written it before, or
even the start, even the fire up wasn't written by a human.
You have to give it some. But I don't know if this is the warm up or not. I believe with 90% he deleted the warm up because it will be meaningless. For sure he should delete it, but I'm not sure. Alas, I think he shall come approached, and the day when little's brain would be attainable. That's interesting. Also, someone has trained it on 100 megabytes of Wikipedia dataset, and that was the result. It started to raise my decision for the majority of Arab countries. Why Irish language? Why? Yeah, it also tries to put citations.
Or it doesn't exist.
So it started to insert some
Human you.
It's very strange. Also, it can generate XMLs. It writes any data, but still does not skip closing the headers. So each header is closed. It learns this and the spacing, and it understands that ID should be a number, so it shouldn't be a text. Username is Paris. Okay, Arabic algebraic geometry. This is a mathematical proof that is meaningless.
Very good for us.
But for it maybe has some meaning. So it's trained on lots of LaTeX text with equations, and it was asked to generate LaTeX folder according to what it has been learned on, and that was the result. Also another sample. I think if you show this to someone and tell him the machine has generated this, he will not believe. It can generate code, by the way. This is a code generated by, it's meaningless code, but at least you can notice that the syntax is correct.
It can.
Yeah, maybe it caused bugs during runtime, but the syntax is not a problem. So this is a nice link I have showed to you.
AB names.
It has baby names. So we are about to finish. Sorry for exceeding. We are about to finish. We have different architecture with neural network. This is the one-by-one architecture that we have used too. Without any recurrent neural network, you have an input, and for this snapshot of the input, you have a desired output, one-to-one. But usually, when you have RNN, you can have different architectures. You may have one-to-many. For example, for image captioning, given an image, give me a caption. I will show you some astonishing results about this. You can give it an image, and it will tell you this is a boy playing with his toy, red toy, and I will show you some results. So this is example of one-to-many, and this is example of many-to-one. Many-to-one is like the steering angle prediction. Given a video, what is the steering angle decision? Also, many-to-many, like machine translation, you have some text and you need to translate it with many words. And okay, the main problem with sorry. If we want to train this neural network, it is the same as we have been done in our backpropagation proof. This is the unfold of it. Here, the output of each. Here we are concentrating in a specific neuron that we are training. Let's assume we are interested in this neuron. We want to train this way. So S3 is this output, which is equal to the activation function of the net. What is the net in this case? It is W multiplied by S2 plus U, these weights, multiplied by the input at time C. And what is Y? Y is the output. Here we have a softmax function. So Y is the output of Z, and Z is S3 multiplied by V. And you can define E as the negative log likelihood. So Y hat is the prediction, Y is the ground truth, and you can start to differentiate this log equation, and you will end up with a chain rule that is very simple in case you are differentiating with respect to V, but it is very long in case you are differentiating with respect to W. As you can see here, the chain is getting too long, and this will cause that if these numbers are bigger than 1, eventually we'll have a very large value for it's dE by dW. And if they are smaller than 1, you will get 0. And this is known by the gradient vanishing or the gradient saturation. And how to solve this is to modify the RNN architecture so that the output of the neuron is not only f of net. Okay, the output is f of net plus some leakage. It's like the neuron is gated. It has some gate that leaks part of the input. So the output of a neuron is f of net plus some factor multiplied by net. Okay, it's like it's a gated network. So gated recurrent neural network is an important part of RNN, and the factor of gating is also a learnable parameter. You let the network learn it with back propagation. A famous type of gated recurrent neural network is the Lsdm cells. Lsdm, this is an Lsdm. It's a special kind of neuron. And instead of this is the normal neuron. It takes x plus the previous value of itself and applies the activation function. This is the out. But now we will take part of the input and pass it directly to the output, and we will take some other part and pass it to the tang, and so on. So it adds 1, 2, 3 more parameters that should be learnable. So now you are not learning only the weights, you are learning more parameters, and these parameters, if the parameter alpha that is multiplied by the net, the leakage parameter is 0. So the network decides to rely on the activation function out. But if it is very high, so the leakage is very high. How much leakage it should get? Let it figure out. So alpha is a learnable parameter, and this is why this network, this type of cells, can learn on its own whether it should consider long-term dependencies or short-term dependencies. Lsdm is standing for long-short, means long and short-term memory cells. And now we have finished. The last thing I want to show you is this application. I promised to show you in which architecture this was done by RNN, one-to-one or many-to-many, or someone answer me. Someone raise his hand and answer me. To be the last question. This is the last slide. Two young girls are playing with Lego toy. By the way, you can download the source code and play with it. I believe it is based on TensorFlow. Yeah, TensorFlow.
They're not all with CNN.
Sorry?
All not. They are all with CNN.
Yeah, this is a good question. I'm sorry for skipping this. You can always combine CNN with RNN because RNN is usually used at the fully connected layer. At the MLP, the multi-layer perceptron at the fully connected, you should put the recurrency there. So CNN is used as a feature extractor because it's very efficient for images, and you need to benefit from all the history. So let's do some recurrency in the fully connected part. Okay. So which architecture is this? One-to-one or many-to-many or? Sorry.
Single images or videos?
Yeah, from single image you should get a caption. One-to-many, yes. From a single image you need a sequence of words. Okay? So, thank you so much. I'm very sorry for this quarter hour extra. And have a nice evening. It was very nice training. And don't forget the attendance and the evaluation. By the way, some of you didn't write their attendance yesterday. So it's here.
Was there a attendance today?
Yes. For each day, there is a different.